geometry right here has two disconnected asymptotic boundaries, and so this is a space-time wormhole. So in conventional ADS-CFT, geometries like these space-time wormholes, lead to the so-called factorization problem, first introduced by Maldacena and Meos. So, for example, suppose we try to compute a product of two thermal partition functions for a theory like n equals 4 super Yang-Mills. Using the boundary Hamiltonian, this quantity is clearly just a product of two individual partition functions. We take trace e to the minus beta h times trace e to the minus beta prime h, and it's a product of two partition functions, and that's it. However, if we use the gravity approximation to the bulk theory, it seems that when we compute these two partition functions, we should sum over a larger set of geometries than just those summed over for the separate partition functions. And for example, space-time wormholes are naturally included in the computation of two partition functions, but not in the computation of one of the individual partition functions. So here as an example, we've shown two partition functions, and we've got two disconnected things like the Euclidean black hole plus a space-time wormhole. And if these extra geometries from the space-time wormholes give a non-zero contribution to the path integral, what we thought should be a product of partition functions doesn't seem to factorize anymore. So that's the factorization problem. So perhaps space-time wormholes should just not be included in the bulk path integral. If that's the case, what principle in the bulk theory would instruct us to discard them? Maybe somehow the contributions of all these space-time wormholes sum up to zero. However, there are indications that these space-time wormholes should play some non-trivial role. So there's some quantities for which there is no factorization problem, but space-time wormholes seem to give very sensible answers. And this is even the case for some theories with a fixed Hamiltonian. So two examples would be the page curve of Hawking radiation and the ramp in the time-averaged spectral form factor. So for both of these quantities, you can compute them and get sensible answers with space-time wormholes, but those same geometries, those same space-time wormholes give factorization problems in very closely related quantities. So in this talk, we're going to often use as an example this spectral form factor, which is you take this analytically continued partition function, z of beta plus it, where t is time, or a fixed energy version, y of t, where we fix the energy in some smooth window. So let's take the modulus squared of this quantity y. And for a chaotic theory like n equals 4 super Yang-Mills, we expect that this function is pretty noisy at sufficiently long times. So I've drawn here in red this noisy curve. And so these longer time scales is pretty erratic. But what we can do is take the time average, where we average over small enough time windows, but not too small, so that the time average is smooth. So here I've drawn in black the time average, this thing we call a ramp, which is grows linearly. So if we try to compute this time average in gravity, we can use a wormhole. The wormhole gives what we expect, this linear function for the time average. Similar things hold for higher moments. They're also, you can calculate using wormholes and you get sensible answers for time averages of higher moments. So because of the time averaging, this time average spectral form factor doesn't need to factorize, so there's no factorization problem. And even for conventional non-averaged ADS-CFT with a fixed Hamiltonian, we expect, based on random matrix universality, that the wormhole provides the correct answer. However, as we remove the time averaging, this noise becomes important. It's actually very large. It's about the same size as the average signal itself. So this noise is something big. In a bulk description, we can ask, how do we describe the noise? And in a bulk description which captures this noise, does it also include wormholes? Or do the wormholes, if you want to describe the noise properly, do you have to throw away the wormholes? So one of the things we're going to be looking for is something like an effective description of gravity with this microstate noise, which captures some aspects of the noise, at least, maybe not the full details of the noise, and includes wormholes. So wormholes aren't just thrown away. So this is maybe roughly analogous to something like hydrodynamics with quantum noise, or souped up to include Brownian motion. So it might be helpful to discuss a computation of the spectral form factor in a non-gravitational system. And so we're going to look at chaotic billiards. And here I've shown a little billiards table, and this, these red lines are chaotic paths on this billiards table. So to compute y of t, using the path integral, we sum over periodic paths. We can do it by saddle point. And we find a sum over all the periodic orbits of period t. So we can think of the y of t as coming from two parts. There's a smooth part that comes from so-called short orbits, which are infinitesimal paths. And this part leads to contribution that is related to the smooth approximation to the density of states of this billiard system. We also have a sum over these long orbits for t being a very long time. So the long orbits know about the finer structure of the energy spectrum, not just a smooth approximation. And so we're summing over all these phases from the actions of these orbits. And for long times, the actions are large. And so these phases are like essentially random. And so this part here gives a sum of almost random phases, which it gives the noisy signal that we expect for y. So now we can take the modulus squared and do some time averaging. So the modulus squared comes from a double sum over the orbits. However, when we do the time averaging, if we treat these phases as essentially uncorrelated, this is an approximation due to Michael Berry, and we remove all the off-diagonal terms, which average out to 0. That leaves just the diagonal terms, and we can take this diagonal sum here and using some general aspects of these systems, estimate that it grows linearly in t. So that's what we expected for something like this time average of the spectral form factor. And so we want to think about this diagonal piece of this double sum as roughly analogous to the wormhole. It gives this linear growth in time for the ramp on the spectral form factor. And as a side comment, this picture breaks down exponentially long times in the entropy. And that has to do with the fact that this approximation of averaging away the off-diagonal terms to 0 breaks down. So this orbit calculation motivates for us a cartoon of factorization and idiocy of t. So instead of throwing away the wormhole, maybe we want to view the wormhole as something like a diagonal part in a sum over something like broken cylinders, we'll call them roughly. And to achieve factorization, maybe we need to, instead of getting rid of the wormhole, add in the off-diagonal terms. And so I ask, is there evidence for this cartoon in a gravitational theory? Does something like this happen in theories that we can calculate with? And so what we'll do in this talk is find that this is a good effective description for some theories. So now we're going to move on to discussing this problem in some simple gravitational theories that are dual to ensemble averages of boundary theories. And this is different than conventional non-average idiocy of t like super Yang-Mills. So while the averages of partition functions shouldn't factorize, if we focus on a single member of the ensemble, we'll find factorization. So to understand how this works and how we calculate for a single member of the ensemble, we have to review some formalism, which relates the gravity path integral with space-time wormholes to the quantum mechanics of baby universes, closed universes, and ensemble averages. So we're going to follow the approach of Marolf and Maxfield, who in turn built on old work of Coleman, Giddings, and Strominger. And to illustrate this formalism, we're not going to use a very complicated theory of gravity. We're going to use a very nice, simple model, which was introduced by Marolf and Maxfield. So this simple model is it's a topological theory of two-dimensional surfaces, and these surfaces can have circular boundaries. And we want to think about the circular boundaries in this theory as roughly analogous to asymptotically ADS boundaries. So, for example, in this theory, we can calculate quantities which I'll call z sub k, which is the sum over surfaces with k circular boundaries. And so contributions are weighted by their Euler character. And so we can see here, this z sub 3 is the path integral with 3 boundaries. And this looks just very, very roughly like the path integral, which would compute k partition functions. So we have, for each copy of the partition function, we have a periodic thermal boundary. And we can connect them with space-time wormholes.
Is there a partition, sorry, is there a Hilbert space associated with the circle? How seriously should I take the statement that this is a topological field theory?
Yeah, so there's something which is maybe a little confusing, which has to do with how you normalize these boundaries. With an appropriate normalization, yeah, it does look like there's a Hilbert space. And so the ensemble of boundary theories, which I won't really get into in this talk, is just like they're labeled by the dimension of this Hilbert space.
Okay, in standard two-dimensional topological field theory, one of the most basic things you say is that to a circle you associate a commutative Frobenius algebra. What is that in this case?
I don't know. I'm actually not going to be taking advantage of the boundary description at all for this model. Mostly, I just want to take advantage of this, just the general structure of the sum over spacetimes. Okay, so because of the contributions of space-time wormholes, these ZKs just don't factorize. But instead, they behave more like correlation functions of an operator which we call Z hat. So for example, the 3-boundary quantity, we want to think about it as a 3-point function of the Z hat operators. So what do we make of this? What are these correlation functions? What's the Hilbert space in which these operators act on? So more often, Maxfield told us that we should think about these operators Z hat as acting on the Hilbert space of closed universes. So what is this Hilbert space? So to describe this Hilbert space, what we want to do is we want to start with a special state, somewhat like the vacuum state of the closed universe, is called the no boundary state, sometimes referred to as the Hartle-Hawking state. And we can take the no boundary state and act on it with the Hermitian operator Z hat to get more states. And to define these states, we relate their overlaps to the path integral. So we say that something like this, Z hat to the K in the no boundary state, that is computed using as ZK, which is this path integral computation. So this fixes all the inner products between these states here, which we take to span the entire Hilbert space. So here's just as a couple examples. On the left here, I have an example geometry contributing to something like an overlap between two states. Here I have Z hat cubed acting on no boundary, and here I have Z hat squared acting on no boundary. So I'm going to, throughout this talk, when I write overlaps of states, I'll have like the bra on the bottom, and so the ket on the bottom and the bra on the top. And we can have, so Z hat cubed has 3 boundaries, Z hat squared has 2 boundaries, and we sum over all surfaces with these boundaries to compute this overlap. On the right here, I've drawn an example contribution to the 1-point function of Z hat in some state psi. So psi may be some general superposition of these Z hat to the power on the boundary states. So to represent these states psi, I have a couple boundaries shown, but then I have ... to represent, I'm not sure what else I'm summing over to represent the state.
Sorry, in this example, when you go from 3 circles to 2, are you summing over all Bordisms from 3 circles to 2, or you just drew one geometry?
Yeah. This is just one example contribution. I'm summing over all. Yeah. So here are these red lines. These are supposed to say, okay, the thing under it is a normalized state, and the thing above this one is a normalized state. And so to compute this 1-point function, I can sum over all surfaces which connect my, we'll call it a probe boundary, z hat, the observable in the correlation function, to these state boundaries living on either side of these red lines. Okay. So correlation functions in the no boundary state don't factorize. And so those are the things we identify with the ZK, the things which we would maybe naturally think of as what you want to compute, what you do to compute partition functions. On the other hand, we can look at states that aren't the no boundary state. In particular, we can look at eigenstates of the operator z hat. And so correlation functions in an eigenstate of z hat will obviously factorize. They're simply equal to the eigenvalue raised to some power. So these eigenstates of z hat, sometimes referred to as alpha states, and they're generalizations in other theories of gravity as well. So computing in an eigenstate, we'll call it z naught, with z naught the eigenvalue, corresponds to picking out a single member of the ensemble of boundary theories, where the partition function z has a definite value z naught. So the no boundary state provides a natural ensemble distribution over this ensemble, though we can, of course, pick any other distribution we want. And so I should mention this relationship between the states of closed universes and ensemble averages was first discussed by Coleman, Giddings, and Strominger. So one thing we're going to do in this talk is think about these quantities, these correlation functions and stuff as overlaps of states. So we can take a general state psi and write it as some function psi of z hat acting on the no boundary state. Then a correlation function in the state psi, we can write as an overlap of these two states here. Z to the k acting on the no boundary state, and psi squared. So we take this function psi, square it, and act on the no boundary state. So these are, importantly, not normalized states. So here, as an example, I've shown z squared overlap with psi squared. This is the 2-point function of z in the state psi. So in this picture here, I've drawn it like I will do. As an overlap, I have the ket on the bottom, bra on the top, and the purple line here, I'm going to use to represent things which are psi squared. So on the bottom, below this purple line, I have some boundaries, and I have a dot, dot, dot to remind you that I'm not showing all the different boundaries, which I use to create the state psi squared. And in this overlap, I sum over all surfaces, connecting these two z boundaries to all these boundaries that create psi squared. So computations in this state, an eigenstate z naught, will involve many extra closed universe state boundaries. So below this purple line, we'll have to sum over all sorts of numbers of many extra boundaries. So the computations of like a 2-point function in an eigenstate look very different than what you would normally think of as a computation of 2 partition functions. Usually 2 partition functions has 2 boundaries, one for each partition function. But now we're adding all these extra ones. So we can ask, how do these extra contributions allow these quantities to factorize? Is there any simple structure behind it? So here I've drawn a little picture with summing over all sorts of surfaces that look like this with these 2 z hat boundaries, but it's supposed to turn into a square. And the thing being squared is just 1 z hat boundary connecting all these guys. So one issue is that these we're supposed to sum over all surfaces, including higher genus surfaces. And those higher genus surfaces complicate the story. And so it's not clear how going back to this broken cylinder picture inspired by the periodic orbits, it's not clear how those could fit into that story. One thing that makes that even more complicated is that in an exact eigenstate z naught, you might hope that there's a nice genus expansion in this theory because we've weighted contributions of surfaces by their Euler character. But in these eigenstates, the higher genus surfaces are actually not suppressed order by order. So that might complicate things. However, even though these higher genus surfaces are pretty important for some things, and they lead to things like the discreteness of the spectrum of this z hat operator. We'll find that they're unimportant for approximate calculations of simple correlators, just a few z's. And so we're going to be able to understand an approximate version of factorization without the higher genus surfaces. So assuming this for now, we'll further simplify the model by not just summing over all topologies, but summing over just the simplest topologies where the connected components have the topology of a disk or a cylinder. And we're going to refer to this disk and cylinder model as the Coleman-Giddings-Strominger or CGS model. So in the full model introduced by Morel from Maxfield with all the higher genus surfaces, the spectrum of the z hat operator is discrete. And the no boundary state is a Poisson distribution in that eigenbasis. In this disk and cylinder approximation, we ignore this discreteness and we approximate the no boundary distribution with a Gaussian. And so the center of this Gaussian is described by the disk topology, and the width of the Gaussian is described by the cylinder topology. So we can see that because the 1-point function in the no boundary state is described by the disk, the connected 2-point function is described by the cylinder. So one of the tools we use is instead of an exact eigenstate of the z hat operator z naught, we'll use an approximate eigenstate. And so while an exact eigenstate focuses on one of the discrete eigenvalues of z, these approximate eigenstates will focus on many but not exponentially many discrete eigenvalues. So in these sorts of states, we find that the disk and cylinder approximation works well. And so here in this picture, what I've done is drawn a couple wave functions. On the bottom, I have all these discrete eigenvalues of the z operator. I've shown these wave functions. So as I've just told you, this sharper Gaussian function here is the wave function of one of these approximate eigenstates. In yellow, I've drawn the no boundary state, which is much, much wider. That covers exponentially many eigenvalues. So the failure to factorize in these states is basically measuring the width of the wave function. So the width of this no boundary state is large. So the failure to factorization is large. In these sharper states, the variance of z is very small. So in this CGS model with disks and cylinders, the operator z hat behaves like the coordinate of a shifted harmonic oscillator. So it's useful to introduce creation and annihilation operators, such that z hat is like a disk, which tells you the shift, plus a dagger. And these a's annihilate the no boundary state. So then we can think of a dagger to the n acting on the no boundary state as an n universe state. So as an example, what we can do is take the state z hat to the k acting on the no boundary state, or just what we've labeled zk, and running the z's in terms of creation annihilation operators, we can see that this is a superposition of states with at most k universes. So here for z squared, there's a component which has no universes. This is proportional to the no boundary state. Those come from the contribution of two disks capping off our boundaries, or a cylinder connecting the two boundaries. There's also a component with one universe, and there's a component with two universes. Now, what this lets us do is say that these correlation functions of z hat to the k involve the components of this state, this psi squared, with up to k universes. And we can see that by saying, okay, this correlation function is this overlap of two states, and insert a complete basis of states in this number basis. And because this state is only supported on these n's up to k, then we only need these components with n up to k.
Can you remind us what you mean by psi squared?
Oh, yes. I'm going to go back to this slide because it's somewhat important. Sorry. So psi squared is if you take a state psi, we'll be able to write as a function psi of z acting on no boundary. Yeah. Psi squared is you just square that function and act on no boundary.
So in other words, you're just taking the bra and the cat and pulling them together, psi squared.
Exactly, yeah.
Okay, thanks.
But suppose that the no boundary state was annihilated by some operator.
Mhm.
So psi of z hat is ambiguous in your definition. We could write psi of z hat plus O, or O annihilates.
Yeah, that's absolutely true. Yeah.
And then psi squared is not well defined, because if I expand that out, there'll be a term in expanding out the psi plus O squared, there'll be a term O times psi of z hat, which might not be 0.
Yeah, it's true that this psi of z hat. So there's a lot of states which are, so Moroff and Maxfield talked about this a lot, and the words they use to describe it were null states. They said there's a bunch of states that are just related by null states, and that corresponds to different representations of the state, different size representing the state, and that doesn't cause us any issue in this.
Why not? It looks like the psi squared is ill-defined because of this.
Well, for a specific choice of psi, we can calculate, and we can find some. What we do is we use specific examples where there's no issue.
Is the answer that in this case all operators you're interested in all commute with each other?
So that's important in allowing us to represent all these correlation functions as these overlaps, just by, as you say, commuting past these.
But doesn't that answer Greg's question also, if you define all the states that are annihilated as 0?
Well, indeed, if O commutes with psi hat, then O times psi hat times no boundary will indeed be 0.
Oh, yeah. Sorry, yeah. So yeah, it's true that in this case, of course, there's one operator, but in the more general case, we're going to think about maybe many z hat operators, and the only observables we're interested in are z hats which commute with each other, and size as functions of those z hats which commute with each other. So I think that's not an issue for that reason. So yeah.
Frankly, I'm just translating all your formulas into the simple harmonic oscillator and then trying to picture. But that wouldn't be true in the simple harmonic oscillator. So the simple harmonic oscillator is not a good model for your.
Well, the simple harmonic oscillator has observables which don't commute.
Exactly.
And we don't think about observables like that. So it's because we only think about these z hats. Yeah. It's true. We shouldn't really think about this system as the same as the harmonic oscillator, because there's all this extra stuff going on in the harmonic oscillator, like non-commuting observables. I think I'm having some tech problems. Let's see, I'm gonna share my screen again. Okay. Okay, so let's see. So now we're interested in these correlation functions, and we're going to use these overlaps to describe them. Jeez. Okay, I'm going to try to not touch the screen for a minute, just in case it freaks out. Okay, so let's calculate the 1-point function of z in a state psi. Now, first we include the disk, and now we and also the cylinder. So we can think about the z hat as a sum of the terms where the probe z hat caps off on a disk. And in that case, it doesn't feel all the boundaries corresponding to psi hat. and or psi, and they just factorize out, and so you're left with the disk. You also sum over all the surfaces where the probe Z connects to one of these psi boundaries with a cylinder. And using the formula on the previous slide, which hopefully now I can go back to and it won't cause an issue, that term involves the one universe component of psi squared. So in this picture, what I'm doing is I'm saying, okay, take all the surfaces where we connect with a cylinder, and we can think of all these psi boundaries as preparing a state on this cylinder, a one universe state, psi, the projection of psi squared under this one universe component. And so the answer for this 1-point function is a disk plus this projection of the one universe component of psi squared. Something similar happens for the 2-point function. So we're going to subtract off the disk for simplicity. So the 2-point function of Z, there's a contribution where we connect the two boundaries with a cylinder, and they don't feel the psi at all. But there's also this contribution where we take the two universe component of psi squared. So all the surfaces with two cylinders connecting to these psi boundaries, what they do is sum up to prepare this two universe wave function on these cylinders. And so here I've drawn a little red line linking these two boundaries to say this is a two universe wave function that isn't necessarily a product of the two one universe wave functions. So now what we want to do is ask, okay, what property must this state psi squared have to be an eigenstate of Z such that this 2-point function factorizes? Okay, so just by comparing the two expressions we calculated on the previous slide, we see that this two universe component here has to be something like the product of the one universe components minus the cylinder. So what is this telling us? In this computation of the 2-point function, we have the cylinder which normally, without thinking about this state psi, told us that this 2-point function doesn't factorize. But when we add this thing here, this two universe component, such that psi is an eigenstate, then it factorizes. So this two universe component is the thing we're adding such that the 2-point function can factorize. So going back to this picture with the periodic orbits and these broken cylinders, this is roughly analogous to like adding in these off-diagonal terms in the orbit sum. It's a square of something minus the cylinder. But of course, there's no sum here. There's only it's like a one-term sum. So it's a little bit silly to say that. So can we understand this property of the wave function better? It turns out to be slightly more intuitive in JT gravity. So in JT gravity, it's a lot like the models we just talked about. Instead of a single operator z hat, we have many operators z hat sub I, such as z of beta plus it or y of t for different values of t. And just to emphasize, these will all commute with each other. So the y hat of t are useful because for sufficiently different values of t, they behave like independent Gaussian variables in the no boundary state. And so because we have all these basically independent variables, it acts a lot like many copies of this topological model that we just talked about. So if you take this operator y hat of t, subtract off the disk contribution, it creates and annihilates approximately orthonormal one universe states, which we'll label as t. And we'll also use it for more general operators z hat sub I, which create one universe states I. And the Hilbert space will be spanned by n universe states with different i's, labeling the state on each universe. So here's the orthogonality condition between these t states. The overlap between two t states is described by this cylinder geometry with two y boundaries. And it's roughly like a delta function with a t out front. It's actually a Gaussian if you're careful, but we don't really need to think about that. So again, we're going to use approximate eigenstates, not exact eigenstates, to have some sort of control in our calculations. So this disk and cylinder approximation, where we drop all the higher genus stuff, works well for many observables, correlation functions of a few operators in some of these approximate eigenstates. So here, we're ignoring all these higher genus surfaces and also non-perturbative effects in the model, which tell us about the discreteness of the spectrum of the random matrix dual. So one example of something we can do within this disk and cylinder approximation is we can try to calculate this spectral form factor in an approximate eigenstate. And the disk and cylinder approximation works. And instead of giving us this noisy red curve right on the nose, we can get the noisy red curve with some small spread around it because of the non-zero width of this wave function. But importantly, the width of this wave function is much, much smaller than the sort of size of these fluctuations in this noise. So we can approximately get this noisy function, though not quite exactly in this approximation. So our approach is related to something called eigenbrains, which is a method for constructing exact eigenstates in this theory, including the discreteness of the spectrum of the random matrix dual. However, gravity computations in these exact eigenstates are difficult to control. So that's why we're talking about these approximate eigenstates at all. So to connect to this effective description, which I've talked about, it's useful to use an approximately orthonormal basis and label this basis with B1 to Bn. And these numbers B label the lengths of circular spatial slices with zero extrinsic curvature. So they're approximately orthonormal this. And this basis is useful, for example, for talking about this cylinder. We can think about this cylinder between two of these T states by inserting a resolution of the identity in this B basis in the middle. So that we can think of it, this cylinder as two so-called trumpets glued together along this B circle. So here this trumpet represents the overlap between the T state on this asymptotic boundary and a B state in the bulk.
So the trumpet just indicates that you have a change of basis? I mean,
exactly, yeah.
We shouldn't be taking seriously hyperbolic geometry, or should we?
Well, in JT gravity, it's computed using hyperbolic geometry.
So we should be thinking of this as hyperbolic metrics.
Yeah.
So, okay, so as long as I'm interrupting. In the old matrix model 2D gravity story, there was a whole story about macroscopic loop amplitudes.
Yeah.
Is there any relation to that?
Yeah, so these boundaries are more closely related to the macroscopic loops, but I'm not exactly sure about exactly how they correspond. I think it's still a little bit unclear. So one of the things is these boundaries are of infinite size. They're asymptotic boundaries, and
let me phrase it differently. If you look at a matrix model and you study the resolvent,
yeah, that's
a generating function for macroscopic loop amplitude.
Yeah, so that's the thing which corresponds to this boundary. Those are computed. This boundary will be something like trace of e to the IHT, which you can get by using resolvents.
Thanks.
Mm-hmm. So in this B basis, what's the condition on psi squared such that correlation function is factorized? So first, we look at the computation of a one-point function, subtracting off the disk for simplicity. So well, what all these many boundaries in the psi squared state do is prepare a single universe wave function, which lives on this B circle. So we can think about this one-point function with this subtracted as this trumpet with a wave function, which I've indicated with a red circle on this this B circle. The two-point function, again, has a cylinder contribution, which doesn't care about the psi squared. And it now has the two universe component of psi squared living on these two B circles. And again, I've drawn them linked to indicate that it's a two universe wave function, not two copies of a one universe wave function. Now again, comparing these two expressions, we can see that if we want this 2-point function to factorize into a product of the 1-point functions, we need this property of the wave function psi squared to hold. The 2 universe component has to be like a product of the 1 universe components minus this delta function piece, which is related to the cylinder. So again, this behaves like this is the thing we're adding to the computation of the 2-point function, in addition to the cylinder, which allows the 2-point function to factorize. And now we're seeing that it really is behaving something like adding in these off-diagonal terms in the periodic orbits. It's the square of these two things minus the diagonal. So now we're going to talk about an effective model which takes advantage of this simple.
I'm sorry, I have a very elementary confusion. Could you slide back? This process, is this, what you wrote here, is this an amplitude? Is this time evolution? Is it Euclidean time evolution? How should we?
So this picture is just roughly supposed to describe this equation here. Each term is describing one of these terms into equation. So here, the 2 universe component. This blue part here maybe is a little bit confusing, but we can think about it as the blue part. I neglected to draw the remaining part of these trumpets, basically because I'm focusing on this focusing on this B basis instead of computing the overlaps with these Z states. Does that answer your question?
No. What is the blue region here? Is the time evolution or Euclidean time evolution, or some proxy for the inner product that you compute?
Something like the proxy for the inner product is maybe how you want to think about it. So, for example, if I go back up here, let's look at this this thing here. So I'm looking at the 1-point function of Z, and I can think about that as it's the overlap between Z and psi squared, or the state I and psi squared. And by inserting a resolution of the identity in the B basis, I can think about it as involving this B wave function.
What is Z? Is it an operator in this single universe Hilbert space, or is it an operator in the whole set of Hilbert, in the Hilbert space of all possible number of universes?
It's an operator on the Hilbert space of all possible numbers of universes. But what I've done is I've defined it as something analogous to these Z's in the topological model, where it creates and annihilates 1 universe states. So I could write Z as a disk, which is a number, plus a creation operator, plus an annihilation operator.
So this now comes the question that I'm really puzzled by. Should we think of Z as a local operator? What does it even mean to us whether it's a local operator?
I'm not sure what it means to ask whether it's a local operator.
So it creates a whole universe?
Yeah, yes.
Of macroscopic size?
Yes, yeah.
At a fixed time t? Does it create the time that corresponds to it at the same time?
I'm not sure what you mean by at a certain time.
Well, you have a Hilbert space of some number of universes, and time evolves.
Yeah.
Now I act with Z.
Well, I don't have a Hamiltonian.
Does it mean anything to ask at what time it acts, or is this a time of a different universe?
It's a time of a So there's no Hamiltonian acting on the many universe Hilbert space. I could have a Hamiltonian on each universe though.
But then I'm even more puzzled. Which Hilbert space does Zi act on? Because you said it creates a universe.
Zi acts on the Hilbert space of many universes. So for example, so we could take the no boundary state. There's no universes. Zi acts on a no boundary state to create a 1 universe state. And we can take 2 Z's.
Usually when we talk about states and quantum mechanics, we have some kind of time Hamiltonian evolution in mind.
Well, usually you do. In this case, we don't, though, and we don't need one.
Well, you have lots of bras and kits.
Yeah.
Maybe it would help to say, could you just give a concrete mathematical description of a Hilbert space and what these bras and kits are? Is it just L2 of R?
Um,
Or is it a finite dimensional Hilbert space? Or probably not, but is it, I mean,
no,
all
it's not.
Hilbert spaces are isomorphic to, as Hilbert spaces, to L2 of R. Is that what you're talking about?
So what? Well, okay. Like concretely, I have. There's two ways in which I can describe this Hilbert space. One is the set of functions, f of the z i's, acting on the no boundary state.
Usually we talk about a vector space before we start talking about a vector in the vector space, right? So logically, vector space is what you give first, and then you start talking about the vectors in the vector space. So I don't know what this no boundary state is, but it would help if we started with a
Yeah, okay, so think about it.
The fog space style construction. Sorry, I'll let you on. It's just like constructing a Fock space by starting with the vacuum state, and then you have your creation operators, and then
okay, there we go. So the Hilbert space is just L2 of R, which is isomorphic to the what you just described. And so we aren't, but that I was trying to translate everything in terms of the harmonic oscillator, but then I was told that everything commutes.
Yeah, so part of the issue is that a lot of this structure of the Hilbert space we don't use it. We only, basically because we restrict ourselves to looking at observables which commute only. So the Hilbert space is isomorphic to the Hilbert space of the harmonic oscillator.
So it's the harmonic oscillator, and you're looking at the operator algebra generated by A hat?
Yeah.
Yes.
Or by X, really.
Or yeah.
By X, yes, and because I was about to say A hat can't be diagonalized by X. So you're looking at the operator algebra generated by A plus A dagger. Okay.
So maybe, I guess, yeah, I'll continue here. So in this effective model, what we want to do is say, okay, we didn't really make use very much of the many universe aspect of the state size squared. Mostly we made use of the few universe components. And so, for example, for a k point function, we only really needed up to k components of this many universe wave function. So the use of this effective model is to trade away this many universe state size squared for a small number of what we're going to call random dynamical boundaries. So it's a circular boundary with a random boundary condition on it. So to be more concrete and describe this, how this works, this random boundary condition, we'll describe it on slices with these extrinsic curvature 0 and length b. And so then we can describe the random boundary condition using a state on that slice, a not normalized state. So for example, we're going to take the state to be capital psi, and it has random components, psi of b, which are Gaussian distributed. So this capital psi is going to replace this one universe component of psi squared. So if we want to compute y of t in this effective model, we sum the disk and a contribution with one of these random boundaries. And this one random boundary, we have so we include a circular boundary that's a geodesic, and we sum over the length of this geodesic weighted by this function psi of b. So for a single draw of this function capital psi, this reproduces the noisy signal in y that we get for a single instance of JT gravity. Now, because we've replaced the closed universe wave functions, we've replaced the whole capital psi, we've replaced psi squared, which is the many universe wave function, with these dynamical boundaries. We're no longer calculating correlation functions in states like psi. The things we're calculating are now just numbers. So yeah, I really want to emphasize that we're not calculating correlation functions, we're calculating numbers. So as an example, let's look at a computation of many y's, say 5. and we sum over different numbers of these random boundaries, but we only need up to k of these random boundaries. So here I've drawn a few example contribution to this product of y of 5 y's, and we can connect the boundaries together with a cylinder and it cap it off on a disk, have multiple random boundaries, and hopefully you can see that we only would need up to 5 random boundaries max, 1 for each of these guys at most. So if we take the answer for a single y, which is a disk plus a cylinder with a random boundary, square it, and then average over the ensemble of functions capital psi, we can recover the wormhole by gluing together these random boundaries. So these random boundaries are distributions described by the average of 2 sides is like a delta function, and that glues together these boundaries. However, if we want to calculate 2 y's together using the path integral, we should sum over contributions which include 2 of these cylinders with random boundaries and the wormhole. So now it looks like when you try to compute 2 y's, you're overcounting the cylinder because you have an explicit cylinder and an implicit cylinder in this pair of random boundaries. So what's going on is that when you have a pair of random boundaries, that's supposed to be mocking up this 2 universe component of psi squared in the full model. But the 2 universe component of psi squared in the full model had this property that it was like the square of the 1 universe component minus the cylinder. So in order to match with the full model, we have to introduce an ad hoc rule modifying the sum over geometries, which we'll call the exclusion rule. So to understand this, what I mean a little bit better, let's just directly take 2 copies of these dynamical boundary contributions. So here I have a square. That's 2 copies of these dynamical boundary contributions written out in some basis I, which is orthonormal. So I'm just going to artificially separate this sum into 2 pieces. One, which I take this diagonal piece, and here I've subtracted out this diagonal piece from the full sum. So what we can do is we can recognize this this piece as giving a resolution of the identity on the single universe Hilbert space. So that is then equal to the overlap of T and T prime, which is the cylinder, T and T prime. This remaining piece takes exactly the form that we need for the 2 universe component of psi squared, which we earlier made analogy with the off-diagonal terms in this that we want to add to the computation of the 2-point function. So what we're seeing is that this double sum includes the cylinder in this diagonal part. And it's reminiscent of what we've seen in the periodic orbits. So this exclusion rule, which we need to introduce, instructs us to view this diagonal part of the sum over these random boundaries as equivalent to the cylinder. And so we shouldn't overcount the cylinder by including both those terms. So we have a choice. We can include the cylinder explicitly in the computation, but then we have to exclude this diagonal term from the sum over the pairs of random boundaries. Or we can view the cylinder as implicitly included in the double sum over random boundaries and not include the explicit cylinder. And so depending on what you want to calculate, maybe one choice is more useful than the other. For example, if you want to calculate something for which you think the wormhole is going to dominate and play an important role, like this time average spectral form factor, maybe you want to include the cylinder and think about adding in these off diagonal terms, which would average to 0 under time averaging. So looking ahead, we might want to consider a model where this random boundary condition is replaced by a pseudo random boundary condition coming from some chaotic dynamics. And so this is just a rough cartoon of something like a system with a fixed Hamiltonian. And so a simple model of this would involve end of the world brains with some chaotic internal dynamics. And so loops of these end of the world brains would replace the random boundaries. So there's all sorts of different types of end of the world brains we could choose. And one natural choice is similar to the brains previously studied in JD gravity, which live on geodesics, so this B circle. However, this B circle is a Euclidean circle, and so the path integral for these branes doesn't naturally give a function with the right statistics to replace capital psi of B. Capital psi of B is a random wave function, it can be positive or negative, but if you take the path integral for this brane and its internal degrees of freedom on this Euclidean B circle, you tend to get something more like a thermal partition function with inverse temperature B, which is positive and doesn't behave like a random wave function, or the random wave function that we need. So instead, it's maybe better to let these end-of-the-world branes live on periodic Lorentzian circles. And then on these periodic Lorentzian circles, the internal degrees of freedom, the Lorentzian dynamics of the brane's internal degrees of freedom are the things which produce the random wave function capital psi of B. So at least for some choice of brane, this would allow us to write something like y of t as a sum over periodic orbits of the brane's internal degrees of freedom. And if we take two copies of this thing, write it as a sum over terms over orbits of the brane's internal system, we can see that the cylinder is equal to the matched diagonal sum over the brane's orbits. But we don't want to take these models too seriously as models for conventional ADS-CFT, because they don't tell us, they don't have any exclusion rule in them. Instead, they, I think, are useful for providing a cartoon of how something like these random boundaries can be mocked up by chaotic bulk dynamics. So this exclusion rule was just introduced by hand to match the full theory. And so we didn't derive it from any bulk reasoning. We just said, okay, to match the full model, we can't overcount this cylinder. We have to introduce an ad hoc rule. In the full theory with the many universes, the origin of the exclusion rule is geometrical. It's because these partition functions, they share the same psi squared. And so, for example, they can't connect to the same boundaries in psi squared with a cylinder at the same time. But it's tempting to take this no overcounting idea behind the exclusion rule a little bit more seriously. So we can ask, are there other theories described by this effective model in which the exclusion rule arises because the full theory views the cylinder and these matched contributions of the dynamical boundaries as sort of equivalent in some way, two descriptions of the same object. I'm not sure the right words that would be appropriate for this, but like something like a quantum equivalence or duality. And this is reminiscent of some recent work by Eberhardt, which I'll mention a little bit later. So the SYK model provides a possible example of this. So in the SYK model, there's random couplings, the J with some set of indices, and we can average partition functions over these couplings and find a nice path integral representation using G sigma collective fields. So they're bilocal collective fields. So if we take two copies of the partition function or Y, average over the couplings, we have a 2x2 matrix of collective fields. There's same side ones, left, left, and right, right, and off diagonal left, right collective fields. So the G sigma collective fields are closely related to the JT gravity approximation of SYK. And this left, right collective field is related to space-time wormholes. If we don't average over the couplings, instead focus on a single choice of couplings, partition functions then factorize. However, we can still introduce the G sigma collective fields in that case. We can introduce G sigma collective fields, integrate out the fermions, and have a more complicated G sigma integral representing these partition functions. In that case, we can choose to introduce or not introduce the left-right collective fields. So the result of the calculation is the same whether or not we introduce those fields. So in some sense, they do nothing. So the computation of a pair of partition functions with or without the left-right fields in SYK is analogous to computing the square of the one-point function or the two-point function in JT gravity or something like that. One of these computations, the two-point function, has a wormhole. One of the computations has the left-right collective fields. The other computation doesn't have a wormhole. So this gives an example of an equivalence between the wormhole and these matched disconnected configurations. The left-right collective field replaces some sort of matched set of configurations for the disconnected quantities.
So
Now,
I have a question. Are you discussing here a concrete calculation, or?
Yeah, so maybe I don't have very much time to talk about it, but so what we've done is we've used the a technique similar to what we did with JT gravity, where we use approximately fixed couplings, in which case you can have some amount of control over the G sigma integral, and there you can actually say some things that are concrete, and find some sort of version of this effective model that applies to SYK.
I mean, the reason I'm asking is because I understand the change of variables to G and sigma when you average over couplings. If you don't average over couplings, I'm not sure what.
Oh, yeah. Yeah, you can do it explicit. It's just like to find the, maybe I'll say this. You can introduce the collective fields, and have the fermions at the same time. So you can have the collective fields and the fermions, where the collective fields play no dynamical role. They don't really do anything. If you integrate out the fermions, then the collective fields which are left over become non-trivial. But you can't really, in practice, integrate out the fermions unless you average over the couplings.
Okay.
You could, in principle, though, and find you don't know how to actually write down an expression for the action for the collective fields. So what we've done is we said, okay, we don't know how to, in practice, for a fixed set of couplings, integrate out the fermions and find the action for the collective fields. But what you can do is find sort of an approximate version of the action using these approximately fixed couplings.
By approximately fixed couplings, do you mean like there's a fixed part plus a like small random part for each of them or something like that? Or you mean you fix some and not others? Like what's
Yeah, so what we do is we basically follow what we did for JT gravity. Instead of fixing the couplings J directly, or saying like making a distribution which is sharply peaked around one choice of J's.
Yeah.
You try to pick a distribution which is sharply peaked around J's which have a certain value of Y of T at some times or something like that. So you fix the coupling sort of indirectly by picking an ensemble which is peaked around values of Y.
Oh, so I see. So you basically condition on. Yeah. Okay. Yeah. You're doing like a Bayes rule updating based on certain observables or something.
I guess so. Yeah.
Probability distribution. Yeah. Okay.
So maybe because I'm basically out of time, I'm going to not go through these slides and go to the discussion. So what might we learn about conventional ADS-CFT like super Yang-Mills from this? Can a variant of this effective description with these few random boundaries, instead of the many wave functions, something like that, apply to super Yang-Mills? So if that's the case, well, there's two obvious questions. There's one, where do these things like the random boundaries come from? And two, where does the exclusion rule come from? What's the bulk reasoning behind it? So for the first question, just as some speculation, perhaps periodic fuzzball configurations, fuzzballs in quotes, big quotes, provide a microscopic realization of these dynamical boundaries. So these would be configurations which maybe look like the black hole up until some region, and like a fuzzball, or fuzzball, what people imagine fuzzballs do in the more general non-extremal case. And you take a periodic configuration of it so it looks like a cylinder. Maybe those are the sorts of configurations which play the role of these cylinders in the effective description. Even if we have some idea of where these extra contributions come from, we need some principle like the exclusion rule to tell us how to replace the cylinder with these matched configurations. So for the tensionless string in ADS3, Eberhardt gives some indications of something similar to this exclusion rule, some sort of equivalence between the wormhole and some disconnected quantities. So it'd be nice to understand this sort of no overcounting principle or equivalence in this model in more detail. And so it's worth saying that the disk, the Euclidean black hole, poses a similar puzzle. In a full bulk description with microstates, should the black hole be replaced by something like fuzzballs in the same way that you can trade away, or in the same way that in this effective model, we trade away the cylinder for configurations with microstates, so these noisy boundaries. Maybe the Euclidean black hole is equivalent to something like some subset of the contributions of fuzzballs. And we have a choice to either calculate with the black hole or trade it away for some fuzzballs. So this is somewhat reminiscent of the short orbits for the chaotic billiards, where you take all these orbits and you pull out a certain subset, the short orbits, and that subset of these orbits gives the smooth contribution to the density of states, just like the black hole, the Euclidean black hole does. And again, for the tensionless string, Eberhard gives indications of something like this relationship between the black hole and contributions of microstates or something like that, fluctuations around the thermal ADS. So lastly, we focused on wormholes which are relevant for these partition functions in the spectral form factor, not things like these replica wormholes or correlation functions. However, it seems plausible that a generalization of these ideas could explain similar puzzles appearing for these other quantities. In these cases, these dynamical boundaries in this effective description must destroy and create particles. So we didn't have any particles in the models we talked about, but those are important for these quantities. Okay, so that's it for what I have to say. I guess I'll leave this up while if anyone has any questions.
All right, thank you, Phil.
Could I ask a question about this G sigma action in random models? I think there are many models where it doesn't give the right answer due to replica symmetry breaking. So just looking at the G sigma action and basically solving the Schwinger-Dyson equation might not actually give you the right answer. You have to look in more detail at the spectrum of the theory.
Maybe I'm a little confused what you mean. Some models, like, is it like, you're talking
like, for example, variants of SYK where there are bosonic fields.
Oh, okay.
It usually manifests itself in formally complex scaling dimensions when you try to solve for, say, scaling dimensions of bilinears. And
okay.
So, does this connect at all to what you're saying?
I don't think it does.
Saying?
So for the usual SYK model, this G sigma integral is past some pretty non-trivial tests.
Yeah. No, the basic SYK is fine, but there are many models where it's not fine. For example, the so-called random spherical model, or basically many other things.
Yeah, I'm not sure what that tells us about these questions. Are these models also with random averages?
Yeah.
Okay.
Just take a model where instead of Majorana's you take real.
Just take bosons.
Actually, there is a model where they satisfy spherical constraint, which was explored by Culiandolo et al. Many years ago, like around 2000, and you can view the Kitaev model as just that model with replacing scalars by fermions. That model has replica symmetry breaking. These type of models are studied a lot by spin glass experts.
Okay, yeah.
I think there is so I'm just wondering how generic this is one versus the other.
Yeah, I'm not sure.
Okay. I guess another question could be, if you say, replace SYK model by a tensor model.
Yeah,
There is-
that's a question we've been thinking
So-
about. You can do the same thing where you introduce the G and sigma fields and integrate out the fermions for the tensor model. But one of the things we needed for what we've done is we took advantage of these approximately fixed couplings to justify sort of the G sigma analog of the disk and cylinder approximation. And I don't know how to do that for the tensor model. So it's harder to really say anything about the tensor model because we don't have this tool of the approximately fixed couplings.
Okay, thank you.
But yeah, conceptually there's this. It's interesting to think about that case.
Any other questions for Phil?
Just a small, what does short orbits mean for chaotic billiards?
Yeah, so short orbits really I'm not sure if it's a misnomer, but short orbits means you take the like very short time approximation to the propagator. So
Don't you mean a point orbit?
yeah, I'm not sure. I've heard the term short orbits used, but point orbits might be a better term for it. I haven't heard that term though.
Well,
Yeah, if you
when
take
it
the
comes
short
to
time
path,
approximation to the propagator,
that comes from short paths, which
Yeah.
in the case of path integrals you get by expanding around point orbits.
I see.
mhm,
That's the terminology I'd use.
okay.
Wait, short orbits do they always exist for any chaotic billiard system?
I think so.
The short orbit is literally the point orbit. The particle doesn't go anywhere.
It's just okay.
Suppose you were in Rn.
Mm-hmm.
Rn, the only orbit from a point to itself would be the point orbit that doesn't go anywhere. Because if you go somewhere, you'd never come back. So the heat kernel in Rn has to come from an expansion around a point orbit. What else could it come from? But
Right.
since the short time behavior is universal, it must be that in any manifold, the short time behavior of the heat kernel comes from an expansion around point orbits. Point orbits are parameterized by the choice of a point. So you integrate over the target space, and at each such point, you integrate over short orbits localized near that point.
Mm-hmm. For the simple case of geodesic flow on a Riemann surface of genus bigger than or equal to 2, these short orbits are easy to classify or to know?
They're point orbits. They're not
Yeah, okay, got it.
I thought these short orbits were meant to be for the ramp. Is that not right? So they're not the short
No.
time. No, these are. Sorry, I was not in the talk at this slide. So this is just the short orbits are just the initial decay.
Yeah, and the ramp comes from mostly from orbits which
from-
are actually of period t, where t is on the ramp, so it's rather long.
Yeah, okay, sure. Yeah, okay. So these okay.
I think the phrase, my guess is that the phrase short orbit came from trying to compress short path with orbit. It got unfortunately compressed into short orbit.
Yeah, it confused me for a bit. Yeah.
And is there any hope or attempt to generalize this to three-dimensional manifolds of wormholes?
Certainly, a lot of people are thinking about many of these things in three-dimensional case. Nothing that we've talked about, me and my collaborators. We haven't thought about three-dimensional gravity very much. We've been trying to stick to the simplest cases possible, for which we really have some more understanding of the like we've looked at JT gravity, SYK, where we know what the ensemble is, for example. In 3D gravity, people are trying to understand if there's a ensemble of boundary theories for three-dimensional gravity, and we yet don't know what this boundary ensemble would be. So it's harder to study.
And I guess the first problem is that the boundary in this case would have, I mean, they're different topologies. Circle only is a circle, but with the surface, you can have various genuses in the boundary.
Yeah, that's certainly a big complication.
Although that being said, that there's one very nice example which fits at least with your pictures at the end quite perfectly with where you were giving the special basis by decomposing the cylinder into two trumpets. And for the three-dimensional case, the analog would be quasi-Fuchsian groups. So when they act on the hyperbolic three space, the resulting three manifold is basically an infinite volume hyperbolic three manifold with two boundaries, which are both surfaces of the same genus, but with different complex structures. And you can split this three manifold in the middle, and the boundaries, well, the two new boundaries that you get are essentially coming from the convex core. I mean, there's a well studied theory of this thing by, I guess, Thurston's group of people. They're essentially quasi-Fuchsian manifolds, and this thing is called the convex core.
Okay, convex core, okay.
I believe Juan actually wrote explicit solutions of ADS with that geometry.
So that is why I actually brought it up, because well, Greg at some point suggested reading that. So they suggested that there are Euclidean wormholes which are exactly quasi-Fuchsian manifolds. That was. But the thing is, so in this case, well, in this three-dimensional case, would the complex structure or the geometric structure on the boundary matter, or just the topology?
Matter for what?
Well, for the computations of or writing down these partition functions.
Well, I think it should matter. But
in terms of 3D gravity, the action depends on the complex structure.
I see. So that's okay. That's another problem because there's a huge moduli space of complex structures now. But yeah. Although there is a nice theorem of Bayes' simultaneous uniformization theorem, which for these quasi-Fuchsian threefolds works pretty well. It just basically tells you what the moduli space of complex structures on the two boundaries will be, and it just turns out to be two copies of the Teichmuller space for that surface.
Any more questions? Well, if not, let's thank Phil again. Thank you.